Well, good morning, everybody, and welcome back to our webinar series, which we haven't held for a while. We've been extremely busy here with the pandemic, as I know you all have, but it's great to see things getting back to normal again. Held our first workshop last week, which is a sure sign of return to normalcy. Great to see so many of you here. I'm not going to talk more than a couple of seconds here, just to welcome you all. And our presenter today is going to be Nicola Rosano. And
hello, everyone.
Well, thank you, Nicola. He's online there. So logistics as we go through here, if you open up your questions tab, you can ask questions at any time during the presentation. And I and other people here at Ridley Engineering will do our best to answer the questions. If they're very specific, we will hold those questions over for Nicola, and at various points we will ask him the questions when it's appropriate to start. Otherwise, the questions will be held over to the end. Everybody seems to be doing okay with audio and video, so if you specifically are having trouble with that, then check all your settings. It should be working properly. We are monitoring that here with several logins on our end as well. So again, welcome to everybody. Nicola Rosano is going to be our presenter, and I first met Nicola, I think, about 3 years ago, and curiously enough, that was through our Facebook group where we started having some technical interaction, and I realized that Nicola was a very special engineer with a tremendous grasp of theory, but then with the ability to apply it so that everybody can understand it. And we've just talked on off, on a very regular basis on many different design aspects of converters. He has a tremendous amount of real world experience. He's worked in the automotive industry for quite a few years in different places. He's currently working for Vicor, which, as many of you know, I consider to be a leader of our industry in terms of the packaging and technologies that they come out with. So we wish him well with that new venture. He has done some webinars with us before, and you'll find those at the end of your presentation. You can go click on some of the webinars that Nicola has done. And you will also find in the presentation a link to his 3rd edition of Power Supplies A through Z. So Nicola worked very closely with Sanjay Maniktala, which many of you will know, who is a great personality in our industry, and who wrote many books. So the 3rd edition of A to Z of Power Supplies is available as a free download, which Nicola has made available to everybody. So Nicola, welcome to our webinar, and I'm going to turn the presentation over to you now. Just let everybody know, there's a lot of material here, a lot of very good material that we found. There was nothing that was easy to throw out, so we will go fairly rapidly through it, but of course there will be a recording afterwards that you can watch. And Nicola, I'm now turning control over to you.
Yeah, thanks.
You're welcome.
Why we are always looking for new topologies? I was saying before that the main reason is due to an increase in the overall system requirements, right? In the sense that when a new application needs to be implemented, we cannot think to use always the same skeleton. So starting from the bottom of our staircase, we know that the first task is typically to set an output voltage. And for this reason, any power electronics course starts by analyzing the main 3 basic topologies, such as the buck, the boost, and buck boost, and so on. And you know that the basic topologies, you know that these are inductor-based topologies with simple DC transfer functions that are load independent, right? In particular, in continuous conduction, in continuous conduction mode, while in the discontinuous conduction mode, the transfer function become load dependent. But we could also even invoke the famous force switch buck boost, that is basically a cascaded connection between buck and boost. since it corrects the inherent polarity inversion that is unfortunately part of the basic buck-boost topology. In all three fundamental inductor-based topologies, we have a simple direction of control, right? So to increase the output, increase the duty cycle. And then we landed to the isolation requirements. The isolation requirement allow us to pass from the inductor-based topologies to the transformer-based topologies, flyback, forward, half bridge, and full bridge. In these topologies, we can use the transformer turn ratio to properly step up or step down the voltage, in addition to the classical action that is duty dependent, the fundamental topology refers to. And after the isolation requirements, we have been called to design a more efficient system. So that quest leads us to extremely fast switches, right? Such as the modern gallium nitride or silicon carbide devices, or to inherently more efficient topologies, such as resonant and quasi-resonant converters. Fast switches help to reduce crossover times, right, at the expense of the higher EMI, and hence to reduce switching losses, and therefore helpful at very high frequencies, such as 1 meg or even beyond. But at typical low frequencies, such as between 50K to 150K or even 200 kilohertz, commonly associated with the main AC power converters, and even the one involved in wireless power transfer systems, it is preferred to focus on new topologies, such as the LLC topology or the phase shift full bridge topologies, because these enable, but let's say not necessarily guarantee soft switching. For example, the zero voltage switching. To get zero voltage switching, we make use of the fact that any switched network which appears, let's say, inductive to the source, tends to force the current to freewheel through the body diode of the switch, or its, let's say, its antiparallel diode. So if we turn that switch on after a certain dead time, typically 100 or 200 nanoseconds, we can hopefully ensure that the diode is conducting and in effect bringing the VDS, the drain to source voltage, down to 0 or below to 0 when we turn the MOSFET on. So there is no PI crossover. But a more, let's say, a more emerging requirement is the bidirectionality. For example, charge the batteries from an available energy source, I don't know, such as solar panels, but under certain conditions, say during the night, to draw out some energy residing in the battery and delivering this energy back to the grid, for example. Hence, from this point, also from this requirement, there is the search for a bidirectional converters and the recent attention to the DAB converter. So actually, both converters, LLC and DAB, can combine all these requirements, right? Setting an output voltage, irrespective even from the turn ratio. They can guarantee isolation, they can give higher efficiency, and we can get bidirectionality as well. The DAB converter appears inherently symmetrical, right? And thus attractive as a promising candidate for bidirectionality. And it was probably inspired by the phase shift full bridge, probably, when used with an active secondary rectification stage. But the most difficult part in designing the DAB is not in terms of basic control strategy, as you will see, but in the tricky part is how to properly design it optimally. And this is the purpose of this presentation. DAB means dual active bridge and identifies an isolated power stage in which you can identify two full bridges. And both bridges are intended to be active in the sense that each power switch is turned on and turned off according to the designer's needs. So the primary bridge acts as inverter, and the secondary one acts as a rectifier. So vice versa when you reverse the power flow. So as we can see from this image, we have a primary side with 4 FETs labeled here Q1, Q2, corresponding to the node A, Q3, Q4 corresponding to the switching node B, and similarly on the secondary side we have 4 FETs labeled Q5 and Q6 corresponding to the switching node C, and Q7 and Q8 corresponding to the switching node D. Note also I have positively placed all odd numbers Q1, Q3, Q5, and Q7 on the top. So they are so odd numbers identify high side FETs. Let's start with assumptions. So all the switches have the same switching frequency, and all the switches modulation angles are Q1 referenced. What does it mean? It means that Q1 here is designated to be the master always, and in fact, all other FETs are set up to lag this one, at least in this presentation. Note also that for an untrained eye, the DAB is visually identical to an LLC converter with active secondary when the DC blocking capacitance is present, while its behavior highly differs. The DC blocking capacitance presence, we said the following, even on our Facebook group, is strongly dependent from the adopted control strategy. I will add some details later on, but just for now, let's keep the blocking cap inside. Yeah. The lag between the two high side FETs is D1 pi radians, and since D1 can be maximum 1, the maximum shift is pi radians or 180 degrees. So just for simplicity, D1 here corresponds to what can be called even angle 1. So I typically use this term angle 1 or intra-bridge angle. Also, let's open a little digression here. Also, we will see that D1 equal to 1, or if we set D1 or the angle 1 equal to 180 degrees phase shift, we will see how this situation, this context corresponds to the maximum power capability from the primary full bridge, since let's say whenever Q1 turns on, Q3 is off, which means Q4 is on. Whenever Q1 is on, it's the complementary driving. And full power is possible, although it does, careful here, even if maximum power is possible, it does not necessarily mean that the power is delivered to the load. We will see that in a while. Similarly, when Q1 turns off, when Q1 turns off, Q2 turns on, so Q3 is on for the entire duration too, for the entire duration. And now the currents flows through the full bridge network in a reverse direction, trying to ensure what is called the inductor and transformer reset. Also, to keep the number of variables limited, I assume that the lag between Q1 and Q3 is the same as the lag between Q5 and Q7, the one on the top right. And that means that both full bridges have the same phase shift. So the intra-bridge phase is the same. So Q1, so the shift between Q3 and Q1 is identical. The shift between Q5 and Q7 is identical. Similarly to D1, we know that the assumption I make here is that the lag between Q1 and Q5 is D2 pi radians, and D2 corresponds to what is called angle 2 or interbridge angle. So it sets the phase shift between the primary bridge respect to the secondary, or vice versa. It's up as you want to see it. But like D1, even D2 as well can be maximum 1, right? So the secondary essentially could lag the primary by a maximum of 180 degrees. But if D2 is greater than 1, careful here, or alternatively expressed is negative, in effect, we can think that Q3 is leading, not lagging Q1. So the power direction will then simply reverse. But if D2 is between 0 and 1, the direction of the power flows is always the one shown here. So from left to right. I need to do two notes here. So the first note is that measuring the lag of Q7 in respect to the master switch, that is Q1, we get a delay that is D1 plus D2 multiplied pi. This is the first thing. I mean, the shift between drive signals is reported on the right. So you have just an instant catch about how I'm going to drive the dual active bridge in general. And the second note is that we mentioned that when Q1 and Q3 are offset by 180 degrees, so when we are able to deliver the maximum power, actually it is possible to see, we will see it in a while, it is possible to demonstrate that to get the maximum power into the load, can be shown that the secondary has to have a precise secondary lag of 90 degrees. We will show this in detail. So if the secondary lag is less or greater than 90 degrees, that will reduce the power further. Easy here. So each bottom switch is driven complementarily to its top switch just to avoid shoot-through current. So before I mentioned that due to its nature, the dual active bridge offers some curious scenarios by which the power is not necessarily delivered to the load during a specific time interval, right? So here I selected two angles, just random angles, for angle 1 and angle 2 in order to get the worst case 8 segments voltage on the leakage inductance. This condition identifies the worst case in terms of switching FETs on-off combinations. On the right, you can see all the FETs gate drives plus the leakage current and the leakage voltage on the bottom. On the left, you see, by the way, the leakage current path. So let's start from the timing T1, right? Do you see my mouse, just for curiosity, right? It is visible, my mouse. I assume it is visible. Okay, so let's start by the T1. So I actually removed the blocking cap and the magnetizing inductance because basically they are not relevant for the analysis. I removed the transformer as well because it is just a scaling factor. So in the first stage, so at T1, we have Q1, Q6, Q8, and Q4 that are on. So we have circulating currents on secondary, as you can see here. So no power delivered to the load. Then we move to T2, the second interval time in which we set angle 2 minor or lower than angle 1. So Q5 closes first, then Q3. Later on, I will come back to this assumption here because it is tricky a bit. But Q5 closes first, then Q3, as you can see here. So Q6 moves complementary to Q5, and the power is delivered to the load. Then we have Q3 that closes, so after then Q5, because angle 1 is greater than angle 2. So Q4 moves complementary, Q4 driving moves complementary to Q3. We have circulating current here on the primary and power delivered to the load. And then we have the last timing before going to the complementary transition, in which Q7 that is driven with an angle equal to angle 1 plus angle 2 or D1 pi plus D2 pi closes after then Q3. So Q8 moves complementarily to Q7. We have here fully circulating current actually is 0 in this particular example, just because I set the gain equal to 1. But you get, if you place a gain that differs from 1, you get the circulating current. So in this case, no power to deliver to the load. So complementary transition starts later, and the leakage current starts to become negative. And this is just an example about the worst case 8 segments leakage voltage on the leakage inductance. Here in this presentation, so my task has been to properly present you an alternative approach in designing the DAB converter. So the unique approach is this one, is we start studying a kernel with random values, and then we will apply Manichtala scaling laws, plus using my graphical approach that I'll show you in a while. So our target is to get soft switching as much as possible, lower RMS current, and optimal power shape. I will show you in a while what is the meaning of optimal power shape. And we need to design the leakage inductance. We need to calculate the transformer turn ratio. We need to define the output capacitor, the DC blocking capacitors, and in particular, we need to understand what is the best combination of angle 1 and angle 2. Here on the left, you can see some definitions in which in this presentation I call the VOR is the output voltage reflected on the transformer primary side. So basically, it is the voltage on the magnetizing inductance. Vin is the input bus voltage, and the gain is the ratio between the leakage amplitude voltage extrema, so is VOR over Vin. And be careful to not confuse what I call here to being the gain with the transformer turn ratio, that is VOR over V secondary. So if I switch to the peak, basically this is my this is my V secondary, this is my VOR, and this is my Vin. Okay, just to clarify it better. I'll keep going. So just a quick recall here about the scaling laws. Scaling laws have been brought to our attention by Sanjaya. So I reported here the simple case in which we think just to double the power or double the frequency, but the concept can be easily extended to any number. So we have seen this concept even during the LLC webinar. So to double the power at a certain frequency, we need to halve the inductance and double the capacitance. By the other end, to double the frequency, we need getting the same power. We need to add the inductance and add the capacitance. So I reported here the buck converted simplified formula just to explain, just to recall you this concept. So if we would like to double the frequency here, we are placing a factor 2 here in the denominator. So actually to proper getting an identity by this equation, the inductance should halve. The same thing here. So you can use these two formula as a reference to understand the previous two bullets. There is another guest to the party. There is another scaling law by which if we double the input voltage, it is possible to demonstrate how we are able to quadruple the power. And the proof is here below. So I leave you this short demonstration for you, but it is easily to be demonstrated. Let's go to this slide here. So let's enter into the core of the presentation, right? So we optimally designed a DAB. Here I typically use 3 plots, as I shown even for the LLC. But despite here are slightly different, but this peak will characterize what we will call the plot 1 and refers to the power shapes. Our DAB kernel is highlighted on the top left. of this peak. And here you can see 9 cases I studied by using 3 different values for the gain. So you can see 0.5, 1, and 1.5, and 3 different values for the angle 1. You can see 45, 90, and 180. The legenda is reported on the right. So this plot will help us in select the best entry angles. So we mentioned that when Q1 and Q3 are offset by pi, so 180 degrees, the full bridge is capable of delivering the maximum power. But to actually get the maximum power into the load, we see here that the secondary leg shall be 90 degrees, right? So the secondary leg, or angle 2, is placed on the x-axis. It is visible on the x-axis. So if the secondary leg is less or greater than 90, that will reduce the power further. And it can be also it can be shown that if, for example, D1 is such that the leg is let's say 45 degrees, see the blue curves, the power shape starts flattening out, right? So now the secondary side delivers the maximum power when its leg equals to the primary one. So when D1 equals D2. So if the primary leg is 45, so if D1 is 0.25, the maximum power is obtained only when the secondary side leg is also 45. If the secondary leg is made to vary between the flat power zone, let's say 45 to 135 degrees, the power curve, you can see that remains flat for the gain equal for the blue, let's say for the blue curves. And it is clear that all the power curves are always symmetrical around angle 2 that is 90 degrees. And the maximum power occurs exactly where angle 1 equals angle 2, or when D1 equals D2, always. This slide, so in this slide, so what else does this plot imply, this plot here? There is no point in trying to set D2 greater than D1 ever, simply because the power capability is specified by D1 or angle 1, but can be controlled by D2 or angle 2. We get basically nothing by making D2 exceeding D1, right? Just for the previous plot. So if the primary is limited by a low value of D1, there is nothing we can do on the secondary side to somehow extract more power. So here you can see also a funny way to explain this concept, because it seems easy, but I got the feeling that some engineers didn't catch that. So angle 1 sets the maximum achievable power, while angle 2 controls how much power can be delivered to the load. Here we are with the plot 2, which refers to the RMS distributions over the primary side switches. A similar plot can be extracted even for the secondary side. It is just, we need just to scale the epsilon axis. I didn't place the plot for the secondary side just for simplicity, but the shape is quite similar. The DAB kernel is always the same, is reported on the top left. The legenda is always the same cases, same colors. So here you can see the same 9 cases we got by the same gains and the same values for the angle 1. So careful to the bullets here. So locking the gain, the more angle 1 or angle 2 increases, the more the RMS value increases. Locking angle 1 or angle 2, the more the gain increases, the more the RMS values, the more the RMS value increase or decrease. Well, it is not so intuitive at the beginning, because if we assume to work with the green set, let's assume, for example, to work with the green set of curves, no? We can identify that there is a threshold, let's call it gain threshold, at something around, I see here on the bottom left, 40 degrees, right? It means that if angle 2 is lower than 40 degrees, then whatever different gain respect to 1 I use, it will give higher RMS, right? Because I'm shifting up on the y axis. Even if the gain is lower, as well as the gain is higher. So look at these curves very carefully. By the other end, if angle 2 is higher, so if the x-axis point is higher than 40, then the more the gain increases, the more the RMS value increases. So a statement that is not valid if we work below the gain threshold point that has been identified here. Now, okay, so here we are with the plot 3, in which I report the DAB zero voltage switching limitation. So careful to the legenda reported on the right. Here I have analyzed 3 gain cases, identifying what are all the possible angle 1 and angle 2 combinations which enable zero voltage switching. So we can see then the gain equal to 1. In a while I will play a video here just to show you what I'm referring to. But we can see that the gain equal to 1 enables a greater zero voltage switching area in respect to the other cases. So this plot assures full zero voltage switching for all switches, primary and secondary. In related literature, there are some mathematical formula which assures zero voltage switching, but be careful because they have limitations in the sense that they assume fixed values for the gain and fixed values for angle 1 and angle 2. But to me personally, that was not sufficient. So you could find this map more intuitive because it includes more subcases. I would like to run with you this video that basically in which I play my MATLAB routine to show you how I get this plot here. Okay, so I'm running here my MATLAB routine. This is a recorded screen. And I would like to show you how does the algorithm extracts the zero voltage switching area. So here I'm getting the RMS. Here I'm getting the power curves. So do you see these points are basically the MATLAB algorithm is calculating the steady state for each angle 1, angle 2 combination, and is saying, look, for each bullet here, you are able to guarantee the soft switching or the zero voltage switching for all devices, so primary and secondary. So the green one is with the gain equal to 0.5. The red one is with the gain equal to 1. So you can see that the area is much higher respect to the green one. And then in a while, you should see even the one with the gain equal to 1.5. Do you see? So basically, the gain equal to 1 ensures a greater area. Give me just 1 second. I just turn on the light. Okay, so this basically this is how I extracted in a brute force way the zero voltage switching, and how I can demonstrate with the gain equal to 1 we are able to ensure a greater area. Here you get with the RMS value. Yeah, I can share this routine, no problem. Here on the primary RMS value on the primary, and here we have the power curves. Just to let you know that despite the minimal assumptions possible we made, the angle combinations offers two subcases, right, within the broader category of D1 greater than D2. So the case 1 on the left is when D1 plus D2 is minor, so is lower than 1. The case on the right is when D1 plus D2 is higher or greater than 1. So for this case, we can see that a small edge appears in the switch node D waveforms. The two cases produce different applied voltage waveforms and different time segments too. We will see that in a while, but the point of this slide is basically this one. When and if you will be called to the buggy module, let's check Q7 drive directly, because it is the key. A small edge appears at D1 plus D2 greater than 1. Another question is which one is better? Which case is better? This question is explained in the following slides, but at least intuitively, I would say that the solution which guarantees soft switching, lower RMS value, as well as optimal power shape will be the best. Okay, the rule of the leakage inductance. Okay, so by eliminating the transformer, now I have reflected the output rail VOR, that is VOUT multiplied N, and the load across VOR is actually the reflected load. No, is the load resistor scaled by the square value of the turn ratio. The first thing we see from the simplified schematic is that there would get literally nothing standing between the input source and the output capacitor to properly regulate the voltage or smooth it out, excluding for the leakage inductance. So if we cut out the leakage inductance, we would get a direct connection, right? Input to output with huge spikes, very high currents, and eventually destruction of the system. That is why, for example, in forward converters, we always need an output choke. And it is the same reason why we have an output inductor even in the phase shift full bridge topology, for example. So in a DAB2, we thus have, let's say, a good reason to properly introduce the leakage inductance. For one, so first reason is to prevent the direct input to output short circuit, but hopefully to also produce, let's say, a regulated output voltage, and this is very important. In a phase shift full bridge, we use an output choke, right, as in a forward converter, and also a leakage inductance. So the purpose of the leakage is, however, only to create a soft switching or zero voltage switching by forcing, as we said before, the current to properly freewheel for a certain amount of time through the body diode of effect during the dead time. And in a DAB, by using a relatively higher inductance for the leakage, we hope to acquire control of the output and also to introduce soft switching. So the leakage inductance in a DAB is basically one component for two functions. But the only way we can get it, the only way by which we can get it is probably, let's say, not switching the secondary side in a synchronous way, but controlling the phase shift of the secondary side so controlling the secondary side bridge with phase control, not in a synchronous way. And reversing the phase control will reverse the direction of the power flow. That is basically how the DAB really works. So careful here, because this is not easy to understand, at least initially. So the active secondary, underline this, the active secondary is not used for bidirectionality as a main purpose, but I mean, the bidirectionality feature is something that you get, let's say, for free with the active secondary. But the main reason by which we need an active secondary is to control the power and to regulate the output voltage. By the other end, the phase shift full bridge has lower leakage inductance to induce zero voltage switching. high current on secondary, large output inductor to control the power, like the classical back and forward converter, and all secondary FETs work in a synchronous way respect to the primary. So there is no secondary phase control. So here on this slide, I'm going to test my DAB kernel. So requirements are reported on the top. And this table reports the most common cases, right, for angle 1 and angle 2. On the bottom, starting from the left to the right, you see which case gives more power, which one gives higher RMS, and which one enables zero voltage switching. So you can see that for the case 2, for example, that is here, we are going to leave the zero voltage switching area. So there is a chance that here with the case 2, we are in a quasi, let's say quasi soft switching, but I will show you the plot in a while. Here, I reported the voltage drives in blue for each switch and each case, as well as all currents in dotted red. So careful to the case 2, because we can see that the zero voltage switching is full for some switches, but is quasi for some other switches. It is easily seen by inspection looking at the switch current. Also, the zero voltage switching map, that is this one, has predicted this effect because we are landing here, right? Where is we are landing here. Here we are with the voltages. So you can see the VP in blue, that is the voltage on the left side of the leakage inductance. We can see the VOR in red, that is the voltage on the right side of the leakage inductance. We can see V leakage in green, that is the voltage on the leakage inductance. And on the bottom in black, you can see the instantaneous power as well as the DC power value in dotted black as predicted by the plot 1. All dotted lines are currents or current contribution, let's see this way, while all solid lines are voltages, excluding for the power plot, obviously. I used PSIM to test the kernel performance. So here you can see our plots and predictions are correct. So we can see in both cases, we are able to get an output voltage regulation of 48 volts, while confirming two different power levels because of the different angles combinations. The simulation file as well as the routine is available and free to be shared with you, so no worries. So here we are with the angle selection, and this is completely arbitrary, and I show you here my method, but I'll open a little digression later to explain why it is arbitrary. So in these few slides, you will see my method. So I will share with you my method for angle selection. So have a look at the three plots carefully. All the three plots are reported on the left, while the takeaway concept are reported on the right and reported in red. So from plot 1, we can see that I suggested to select an angle 1 to avoid flat zones, right? To avoid flat zones, so to avoid this condition here. Once angle 2 is called to increase. So potential choices are angle 1 equal to 90, so the green set of curve, equal to 9, yes, angle 1 equal to 90 is the red set of curves. Angle 1 equal to 180 is the green set of curves. So if angle 2, that is the x-axis, is equal to 90 and angle 1 is equal to 180, it is intuitive that we can deliver the maximum possible power from this kernel. See the green curves here. Also, the more the power requirement, so the effective power is, the less the leakage inductance value is because the kernel power is locked, and the more the size is. In fact, we know that the leakage, the real leakage, the effective leakage is inversely proportional to the power scaling factor, but the power scaling factor is given by the effective power over the kernel one. So if the power requirements effectively increase, you can understand the meaning of this sentence. Both bunch of curves at angle 1 equal to 90, so red set of curves, and angle 1 equal to 180, so green set of curves, give a good power shift because I do not have flat zones here, right? While offering a, as we said, a different leakage inductance once the baseline kernel power is set. So by one side, angle 1 could win as a good possible choice because it is able to deliver more power, while angle 1 by his end could win because it is able to offer a lower RMS current, as we will see. Here we are with the plot 2. So we understood that from the plot 2, that is the RMS plot related, we understood that locking the angle 1, if the angle 2 increases, the RMS current increases. By the other end, locking angle 2, if the angle 1, that is the y axis here, increases, then the RMS current increases. And yes, this is true if we assume to work be on the right side of the grain threshold. So you can see that the takeaway from the plot 1 is reported here. So there is a win-to-win between angle 1 equal to 90 and angle 1 equal to 180. From the plot 2, angle 1 equal to 90 wins because we can offer lower RMS. What about the plot 3, the zero voltage switching area? Actually, we understood that if we place the gain higher than 1 or lower than 1, we are actually decreasing the soft switching area, right? So if the gain equals 1, by keeping angle 2 lower enough, let's say below the gain threshold, we can guarantee a lower RMS current, right? By at the same time, we can guarantee a discrete amount of power delivery. So the best compromise is to keep, at least in my opinion, is to keep the gain equal to 1. So the output voltage reflected equal to win. So the magnetizing voltage equal to the input bus voltage. Note also that, as said before, I'm repeating once again, as said before, if the angle 2 is 90 and the angle 1 is 180, we are in this point here, around here. So we are able to guarantee full soft switching. While if we work on this other condition here, angle 2 90 and angle 1 90, we are just on the bottom of this map, so we can lose some soft switching for some switch inside the power stage. So from the plot number 3, the best compromise is 180. Now, if we collect all the, let's say, the observations we made on the 3 plots, we need a trade-off because there is a win-to-win between the angle 1 that is 90 and the angle 1 that is 180. For sure, the gain is equal to 1. This, no one can object on this, that this is the best condition. So what is the trade-off? The trade-off is this one. Keep the angle 1 equal to 180 with the gain equal to 1. So I'm working with this curve here, the dotted green here, while keeping the angle 2, so the x-axis, equal to the power that you get by locking angle 1 and angle 2 equal to 90. It's better if I show you the pattern set here. We start from this point. We land on this point here on this curve here, and let's say I'm intersecting the same power level. The power level is reported here on the y-axis. I'm intersecting the same power level that I get by locking angle 1 and angle 2 equal to 90 degrees. So we start here. So why 180? We start here because this one can give more power. But why we are moving to 90? Because this one can give less, can give lower RMS current. And then we land to this, I call it best entry angles, like in the LLC, I call it the best entry point. Here I call it the best entry angle. So the best working point is angle 1 equal to 180 and angle 2 equal to 26.5. 26.5 is the angle on the dotted green curve by which I'm able to get the same power by using the red set of curves. You can go through this by your own, but I hope that this concept is clear for you. This is the same working point here. Do you see that I'm just below the gain threshold and I'm working with the green set of curves? Why the green set? Again, because the green set, so angle 1 equal to 180 and the gain equal to 1 can give the higher chance to get soft switching and the more amount of power, okay? And here is our best working point on the zero voltage switching map. Now, it's time now to understand how to properly calculate the capacitor. So here you see on the left side the Cout, and you can see here on the right side the CDC block. So concerning the caps, the design is very simple. For Cout, so the output cap, we need to identify the constant current time interval to apply the main capacitor, the capacitor equation that is reported here. From the peak you see on the left, this interval is half the switching period minus angle 2, so it's easy to identify. So once the output voltage ripple requirement is set, you can get Cout value easily or quickly. Careful to the constant current component flowing through the cap. The constant current component is the leakage peak, the leakage current peak scaled by the transformer turn ratio square minus the mean value of the output current. Is pretty pretty intuitive to get it. For the blocking cap, I need to open a little digression here because there is a huge hint, a huge lesson for us from using, in particular, if you use voltage mode controlled full bridge topologies, because you know that the slight inequalities, especially in timing, could cause it is called the flux staircasing and eventually the destruction of the switches. So it's the same situation that can happen in a forward converter if you try to operate with it at 51% duty cycle. Probably you never heard about this condition because it blew up right away. For this reason, it is usually, it becomes imperative in full bridges, including the phase shift full bridge as well as the DAB, to incorporate a large value of the DC blocking capacitor, especially with voltage mode control. The purpose of the large cap is to, it basically does nothing to the high frequency components of the switching currents, or even to the overall theoretical analysis that we made until now. But in practice, it would serve to merely absorb any slight inequalities, say those arising from slight differences in timings on the right and on the left side of the out bridges. The DC blocking cap, by the way, automatically readjusts any sort of applet volt balance. The cap automatically, let's say, adjust any volt second imbalance if present. Let's look at it this way. At the same time, if you are called in your requirements to reverse the power flow, so going from right to left, you can even think to place the secondary side cap to maintain a certain symmetry in your circuit. Two notes to remind. First note is that if you, first note to remind is that if you work in voltage mode, use the large cap, the DC blocking cap. The second note is you can simply remove it by complicating a bit the control, because you know that there is another way to properly clamp the current, preventing this phenomena of the flux staircasing, right? So surely an alternative is to use the current mode control, for example. You can eliminate the capacitor presence while assuring a full current sensing and setting, let's say, its limit according to your requirements. So acting on the control, the capacitance removal is feasible. In this slide, you see how the natural DAB skeleton offers the possibility to properly reverse the power flow without adding components like the LLC, for example. Also, you can think, or in terms of angles, in the sense that you focus on the angles and you check which one is positive respect to which one is negative, which one leads, which one lags. Or in a more simple and let's say intuitive way, you can apply the same concept we talked until now by simply mirroring the FET position. So in this case, Q7 becomes our master FET. And PSIM suggests that this is a good way to think about it. Now, okay, in this bunch of slides, the bunch of slides that I'll present now, I'm going to stress the kernel, applying the load regulation, load step, let's say load step, the bus step, and even another tricky requirement that is trying to guarantee a flat power over a wide V out variation. So this question comes from our colleague, do not remember the name, but we will arrive, I will discuss in a while. So until now, we have seen how the DAB works if tested in a specific working point, right? So in the next bunch of slides, I'm going to present different requirements by showing at the same time why the graphical approach is so powerful. The DAB kernel is always the same. Requirements are reported on top, so you cannot get confusion. Let's start by applying the classical step load, assuming to deliver half power. So this condition is reported in red on the top right of this slide.
Hey, Nicola, we seem to have lost your, can you reshare your screen?
But from how long did you lost it?
Yeah, the screen is not visible. Oh, yes, it is. Yes, it is. I'm sorry.
Do you see it?
All right, everybody can see the screen. It's just me. Okay, go ahead. It looks good.
Okay. So if we need to face a step load, you know we want constant V out, right? While the power varies. So the gain continues to be 1 as initially set. On plot number 1, you see there are 2 solutions to get half power. Actually, they are even more, but I didn't sketch all the solution here for sake of simplicity because that solution should have involved 2 control variables, overcomplicating the concept. So we have 2 cases here, A and B, and we are moving on all curves of the plot 1 with gain equal to 1. Look at the legenda to avoid confusion. On slide 34, you see that on the plot number 2, I reported the same solutions, right? A and B, previously mentioned. And you can see how the solution B is better because it assures a lower RMS, despite even the A solution gives load regulation, as well as on the zero voltage switching map. On zero voltage switching map, you can see that the same solution, AAB, this is our working point, initial working point. These are the solution. And I'm falling on the point B and on the point A in respect to the solution I would like to, the solution I choose. You can see how even in this context, the solution B, as well as the RMS is written here, the solution B is best, even on the ZVS map, because we are able to assure full soft switching. When I say full, I'm referring to all 8 switches at the turn on. Here, I reported the summary table in which in fuchsia, you can see the angle 1 and angle 2 variation according to the specific solution case A or solution case B. The last 2 columns on the right report the circulating current peak. The circulating current is the magnetizing current. And the RMS value is, I show even the RMS value as well here, highlighting that we will record the differences between core losses and conduction losses, because where the magnetizing current is higher, the RMS is lower, and vice versa. If our preferred solution to fight load variations is the case B, as I typically do, because of full soft switching and lower RMS, then we can say that the load, the circulating current is independent from the load. This question, probably I talk about this with our colleague. His name is Yari, probably, and do not remember the surname, but I mean, hope that this slide can clarify what I was trying to say in our private conversation. So if you move for the solution B, that is the best in terms of performance, the magnetizing inductance is load independent, not load dependent. By the other end, if you move for the solution A, that is worst in performance, as I have explained before, you can see that the magnetizing inductance is load dependent. Probably you were in this case. Oh yeah. PSIM confirms both solution A and B give V out regulation. You can see on the right and on the left, I'm able to guarantee 48 volts at 250 watts, so assuring of power. But the one on the right is the best one because of the points I discussed before. So we gave a step load. What happens if we give a bus step? So here I tried to stress the kernel giving a bus step, right? If we need to face a bus step, you know that we want always a constant V out, right? While the power this time shall be constant at its maximum value. So if we locked the transformer turn ratio at minimum bus because the current is higher for the same power, then the gain is forced to vary. And I reported this statement here is not the same like the step load. So the DAB kernel is always the same. All main info are reported on the top in terms of requirements. The bus step is reported in red and reported on top right here. And now to properly identify the angles variation, we should resketch the curves according to this new case. And here we can feel the power of the graphical approach, because we know that from the third scaling law, if we double the input voltage, the output power is called to quadruple. But I don't want to resketch the curves once again. So instead of resketching the curve, we can easily target 1/4 of the kernel power is the same, being careful to focus on the curve with the gain equal to 0.5, because passing from 200 to 400, we are changing intrinsically, we are changing the gain. Doing this way, we see on the plot number 1, there are 2 solutions to manage a bus step. Actually, as the load step, they are more, but they could have involved 2 control variables, so I didn't report here. So let's focus on these 2 cases, A and B. Careful here because it's tricky. Obviously, the legenda is reported always on the top right of the window. On the plot number 2, you can see that the same solutions are reported, A and B, on the top, on the bottom left. You can see how the solution B is better because it assures lower RMS value, despite even the solution A is able to guarantee load regulation, V out regulation, let's put it this way. But if we jump on the plot number 3, it is this one, I have reported appositely the solution A and the solution B, and you can see that in both cases, for this particular design, in particular in the way I have selected angle 1 and angle 2, we cannot assure full zero voltage switching because we are out of the green area, and the green area is the one related to the gain equal to 0.5. But this doesn't mean that you are not getting added switch in soft switching, added FETs in soft switching, because this map is the intersection of the overall 8 transitions. So this map simply say, look, you are out of the green area because your gain is 0.5. So for sure, you don't get all 8 FETs in zero voltage switching, but there is a chance that you get part of them in soft switching. Let's see it this way. Here, PSIM confirms our intuition. And on both cases, we are able to get V out regulation. And the preferred solution is B because of lower RMS. Actually, this is the third. So we gave the step load, we gave the bus step. Now there is another requirement. There is another requirement that is starting to become dominant in, let's say, advanced power stage. In particular, advanced power stage requirements bring us to this case. If we need to guarantee a flat power over V out variation, how we can manage this with VAB, and in particular, how we can use the graphical approach. This question has been addressed by an Indian colleague. I do not remember the name, but it has been a very interesting question, because in chargers, in electric vehicles, for example, this spec of getting a flat power over V out is a requirement, so it is present. You know, this time, for this requirement, we are not looking for a constant V out, while we are looking for a constant power over a specific V out swing. So, as well as the bus variation, this scenario forces the gain to change. The gain cannot be equal to 1 like our baseline working point. And here is called to increase at 1.5 intrinsically, in particular if we would like to maintain 480 watts all over this output voltage swing. So between 48 to 72, we would like to maintain 480 watts. So first, if V out increases, we are forced to change our load resistor, right? Or equivalent load, but how much? Well, scaling laws help us once again on this point, because if V out increases by 1.5 as the gain, basically, then the load resistor should increase with the square value, so 2.25. So on the plot number 1, there are 2 solutions to manage a V out variations keeping a flat power, but getting the same. Sorry, we have 2 solutions by getting the same power, that is 480 watt, but working with different gain, right? So actually, there are even more, as said before, but I didn't report it because that should have involved the 2 control variables. So we land on the following 2 cases here, A and B. And we are moving on all curves with the gain equal to 1.5 as set by the requirements by assuring the same power. Okay, what is the best solution between A and B? Actually, it is possible to demonstrate that on the plot number it is possible to demonstrate using the plot number 2 that the solution A in this case is better because it assures a lower RMS value. What about the zero voltage switching? The zero voltage switching here is the power of this map. On the plot number 3, you see the same solutions A and B previously mentioned, right? So you can see how in both cases we cannot assure full. When I say full, I refer to all 8 FETs soft switching, because we are out of the blue area that is the one related to 1.5 gain, right? So a detailed investigation of the leakage current, even visually, can anyway suggest if there are some FETs which enable zero voltage switching. For sure, from these kind of requirements and from this working point, for sure, not all of them together. SIM here confirms both solution give V out equal to 72 volt, while assuring flat power equal to 480 watts. Here we have a summary in which solution fits, here Herbert the summary underlining which solution fits better a specific system perturbation. Here you find the answers according all previous analysis. For the step load and do-out variation, the controller should act in varying angle 2. For the bus variation, the controller should act in varying angle 1. Could be better. I say should because you can even move for other solutions, but you are not guaranteeing higher performance. I mean, the performance you get is lower, is worst, but it is something feasible. I seriously hope that these examples, with these examples, you catch the power of the combined use of the scaling laws and the graphical approach, because with this you can get a DAB design really in seconds. At this point, a question becomes spontaneous in the sense that is a DAB designed this way over-designed? Well, if we talk about the maximum deliverable power, then the answer is yes. To me is yes, because if we increase angle 2, I mean, if we start from angle 1 equal to 180 and angle 2 equal to 126, if we increase 26 degrees, if we increase the angle 2, we can deliver more power. So actually, it seems that we are over-designing the DAB. So the word over-designed could make sense at the beginning, at least. But what happens if we talk in terms of performance? For sure, the working point identified with angle 1 equal to 180 and angle 2 equal to 26 is the best at the full load, at least, because we assure the best combination ever between soft switching, low RMS, and the lower stress possible. But what happens if I would have targeted angle 2 equal to 90? So as initial starting point, instead of being on the black ballet, I would like to work here. So I don't want to over design the DAB. Is there any chance to work with the higher angle 2, trying to preserve the soft switching? Because if you remember in the previous examples, when we have applied the bus step or the V out variation, keeping the power flat, we lost the overall soft switching. So this answer is a good answer. Targeting a higher angle 2, say 90 degrees, as shown on the plot number 1, that is this one here on the left. Look at the fuchsia circle. You know that the power scaling factor Kp tends to decrease, while the leakage inductance tends to increase in value. First cons in working here. You could say, okay, but I increase the available area to get soft switching if a bus step occurs. And that is true. Even I confirm that it is true looking at the plot in the center, because you're falling here, not here. But the point is that what happens on the plot number 3? On the plot number 3, it means that you are intrinsically accepting to start with a much higher RMS current at the full load, with a chance to preserve soft switching despite it's not sure to preserve it. So keeping into account all these considerations, the answer is yes, the design can be done even by selecting a higher angle 2, paying this choice with higher RMS, getting a chance to preserve soft switching. And now we land on the fatidic question. Is it better to get lower RMS conduction losses or preserve soft switching? This is the same answer I gave to my colleagues. Nothing comes for free, and there is not a unique answer to this question, because angles shall be tuned according a specific application, considering all the requirements, not a single one. But the point is, the more you are able to stay around the point identified in the previous slide, the more your system will be efficient. That's true, because you get full soft switching, lower RMS possible. It's time to write down some DAB examples. New requirements are reported on top. we keep the same V out while increasing the bus and the power. The approach is always the same. I select the best entry angles. I use the scaling laws to extract the electrical parameters. The DAB design can be done in 1, 2, 3, 4, 5 rows. One note here, you can study the DAB kernel you want. You can use mine because calculations are done, but I invite you to try a different kernel. You will land and you will get the same plot identical as mine, just scaled on the epsilon axis value. And as well as the LLC, I tried to explain this concept in the webinar. The scaling factors will differ, while the final values will not change as per scaling factor definition. This is a very important concept. I will not go through calculations here because everything is written on this slide. They are elementary school algebra calculations. So be careful just to the red numbers here, because they identify the kernel parameters by which our new requirements are called to be scaled. PSIM here confirms our intuition is correct. We are able to deliver 48 volts at 7 kilowatts power. So added to the previous questions I received by our colleague, I collected other questions here. So what happens if we have D1 greater than D2? We said before that the angle 1 or D2, the angle 1 or D1 pi radians should always be set greater than angle 2. A key reason is that D1 corresponds, as we have seen, to the power capability of the primary side, and reducing the power capability is counterproductive, right? So the second angle can be varied as you want, but the angle on the primary side, let's keep it at let's keep D1 always greater than D2. Second, if it is possible to check with the simulation, so I invite you to do that in your spare time. It is possible to check with the simulation that if you set D2 greater than D1, the angle available for drawing DC input current is substantially reduced, because the AC circulating current is relatively higher and takes longer and longer to reset. So it is something I invite you to test with the simulation. What happens if we run the DAB in synchronous mode? Instant answer, the power drops significantly. By the way, soft switching is preserved in some cases, thanks to the presence of the inductor, of the leakage inductor. In this case, adding an output choke is essential to control the output voltage as well as the power into our new synchronous DAB, but probably we can go back in time and reinvent the phase shift full bridge. What happens if the gain varies? So if we don't work with the best compromise that is gain equal to 1? Easy answer. If you remember the plot 1, for sure an answer is the kernel power and the leakage inductance vary. Also, the leakage current starts to, let me pass this term, to distorts, is a distorted trapezoidal, starts to become a distorted trapezoidal shape. So below you can find some example. On the left, the gain is lower than 1. On the right, the gain is higher than 1. Angles have been locked to 180 for the angle 1 and 26 degrees for angle 2. On the bottom, you find the useful equation to get the peak-to-peak leakage current component reported in dotted green on both peaks. Not also all solid lines all over the presentation, if I remember correctly, are voltages. So VP, primary voltage is blue, VOR is red, V leakage is green, while dotted signals refer to the specific current. Another example. Last part, we are at slide 51. Last part is reserved to a new DAB design. Same approach. while getting a comparison with an LLC designed for the same application. Results are validated through simulation, so simulation files are available, but I suggest to do that by your own to grasp the difference. Anyway, here I report the main points. Requirements are reported on the top, same approach as per the previous design. So select the best entry angles, calculating the scaling factors, and get electrical values. This operation can be done in seconds. Obviously, this occasion is useful to compare my approach with your one. In sense, feel free to share your design procedure with me if easier, and if it offers in particular better performance. But please put complicated formula away, because the DAB design doesn't need complex math, as you can see. It's just 5 rows design. Let's skip boring calculations. Here I reported everything for more pedant engineers, so everything is reported here. So PSIM confirms we are able to get 800 volt at 200 kilowatts power for the DAB. So the electrical simulation is okay. What about the comparison between the DAB and the LLC for the same requirements that are reported on the top? In this slide, I collected the electrical values and the waveforms for both topologies. In particular, the leakage inductance is higher for the DAB, as well as the magnetizing one. While the RMS current on the primary is lower for the DAB. So actually, if you look at the waveforms, you can see that for V out is perfectly superimposed. So the scaling laws plus the graphical approach has been used for both the LLC and the DAB. The DAB is slower due to higher electrical values, so higher time constants. The DAB has been designed with the best, let's call it best entry angles, avoiding repeating all the time. Angle 1, 180, angle 226. Let's call it best entry angles. Probably I should have done it before, but as you can see here, the RMS current is lower for the DAB. The LLC inductance ratio has been set to be 9, that is very high, just to keep the RMS current very low. And keep in mind that if you correctly design the LLC, you are able to guarantee zero current switching on the secondary side on both transitions, on and on-off. Looking at the switch current, this is just the switch current for the master FET, so Q1. We can see that both guarantee deep zero voltage switching at the turn on, while the DAB offers a lower. This is the primary current for the DAB is lower in peak respected resonant current for the LLC. Here I collected even the efficiency, in sense that my mouse sometimes doesn't work. Okay. Here I've collected the transistor losses. As you can see from the final result, the efficiency seems to be comparable, but it's a mere coincidence, in sense that what I assume is just an assumption. That I assume that what we gain in the RMS with the DAB, that is lower RMS, is gained with the zero current switching on secondary side for the LLC. So the electrical performance is quite similar here, but a cross-check comparison is always recommended for the specific application. What about magnetics, volume, and air losses? You see on the bottom right the magnetizing current according a real design case, as well as the LXI energy half of the energy term that is comparable between both topologies. Actually, the LLC is slightly lower than the DAB one, despite a huge difference in the peak current is present. Actually, the mismatch is easily explained with the difference in the magnetizing inductance. Yeah, time to me to introduce Sunlord Magnetics. Sunlord Magnetics is a magnetic supplier. My interface was Max Soriano, and you can find his email on the bottom right of this slide. Me and Max started working together on wireless power transfer magnetics a long time ago, and once I saw how do they work in terms of fast prototyping versus magnetics manufacturing, I can say they are, to me at least, in my humble opinion, they are one of the most reliable supplier you can get. Max is a good friend, and he kindly went through the magnetics design for me related to this example for both topologies, catching out the following info. You obviously feel free to give Sunlord a run if you are in trouble with your magnetics design. We see here they have been able to perfectly match my requirements, despite not standard. Actually, if I not remember wrong, Max gave me the final data sheet in something like 5 days, 5 working days, something like that. Anyway, the detailed data sheet for this magnetics is free to be shared with the community. And for any question, any technical point, feel free to contact Max because he's a very kind person. Here we are with the takeaway. I leave this table for you, in which I collected the pro cons for both topologies. Yes, so you can read this table by your own. I leave this one for you. Let me go fast here. I don't want to read everything, but feel free to object on points that you do not retain coherent between all these rows. Oh yeah, we are at the end. We are at the end. So as there are even added slides. So let's check the time first. But we are at the end. So the advices that I can give you is check always soft switching. Look at the waveforms. Do not land on complex math, because if you change the FET, if you change the diodes, if you change the application, the math do not work anymore. So simply look at the waveform on your oscilloscope and check if your design is correct. You can use even my MATLAB routine, which give an instant prediction about if you are getting soft switching. Horowitz dominates with his sentence, at least in my practical stuff. Do not use complex equations to understand how any circuit works. You don't need that for the LLC and for the DAB in particular. So sweeping angles, angle 1 and angle 2 gives much more info, and let's combine the scaling laws with the graphical approach. I leave this question for you, because otherwise it's too boring if I answer all the questions. So did you notice that for the DAB, we didn't talk about the magnetizing inductance in respect to the LLC? Why, in your opinion, we didn't call out a specific value for the magnetizing inductance? Let's open this question even on the Facebook group in our technical center. But I think I have it completed. So let me check the time. Ray, could you help me on this?
Yeah, let me steer you through some of the questions here. One question was the files you have for generating the curves.
I can share that file, no problem. Next question.
And I think the sharing of the file, a good place to do that. You can put it, of course, on your website, wherever, but if you can share those on our Facebook group, that's a good way to reach people that will always be there.
Okay.
So that's a possibility. But they asked about both the PSIM files and the MathCAD files.
Absolutely. I would like, I don't know if he's online with us, but I would like to thank even Albert Danforth, which gave me great support on PSIM. I forgot to do that at the beginning. Concerning the PSIM file, no worries. There is this folder DAB on my desktop with all PSIM files and math files. I simply create a zip free to be shared with you. No problem on that.
Okay.
There was even another question. So if we have time, it's just 1 hour and 40 minutes, right? So better than our prediction, right?
Let's yeah, that's really good. Yeah, for those watching, many of you will be feeling overwhelmed. This is a new topology, it's a new concept. There's a lot to do. I suggest you go and read the third edition of Power Supplies A to Z. I believe you treat the DAB converter in there. So start there.
Yeah, there are some plots in the book that have been not reported for time reasons, basically. So there are some plots that are, let's say, not published, like the RMS one. This one here is not published on the book, as well as the Zeta map. But I agree that the third edition is a good, let's say, reference to keep on your desk if you would like to run with this.
And I would encourage you, for people who are looking for background on this converter, as Nicola has mentioned, don't get buried in the math. If you go pick up some research paper and like throwing,
you don't need that.
You don't need that, right? But some of you, of course, enjoy that. One of the questions we had was, well, I really want to go back to first harmonic analysis. I enjoy that, and so for the 1% of you that like that, by all means, but you don't need that to understand this converter. Next question, which I will get rid of this one because I know you hate this question. Which control chip are you going to use to control the DAB? So go on, deal with that one.
We need to control 8 switches if in the best case. Actually, when you are called to parallel to DAB, let's say current sharing, I mean, it's something that with analog is not possible. I mean, I wouldn't go with analog. So any C2000 or equivalent family or similar is good.
Right. So when you launch into this new converter, you are inherently taking on digital control, you're taking on firmware, software, and your grouper that's going to handle all of that. So I have yet to see an example of this that uses any analog control. It doesn't mean they're not there, but I haven't seen it. Can you see the questions, Nicola? There's not that many left, but there are some.
One moment, because I went. I mean, I followed your advice in working in split screen, but one moment. I do not see questions. I don't know why. So my chat is stuck on the hi Nicola, I can hear you at 5 p.m. So it's 3 hours. I mean, I'm not able to read the question. So I know that there was a guy, do not remember the name, that asked for the dead time effects. So yeah. if this one is included in your bunch of questions, let's run with this one. Otherwise, let's discuss later. This one, it's up to you.
Okay, sounds good. Why don't you go to that slide? Yeah, because there were several questions on the dead time effects.
Okay. So I reported this question just at the end of the presentation because this demonstrates that basically you are working practically on the converter. I mean, it goes out of the classical theory, so as you can see here, for the dead time effects, you can see that. Oh, let me in full screen. Okay. Do you see my screen, right?
Yes.
Okay, so here I appositely gave 1 microseconds dead time between driving voltage. So it's 10 times more the classical one. So as you can see, if you focus on the voltage node VA, but the same concept can be extended even on VB, when the leakage current is lower than 0, then the voltage node here is high, as you can see here. You see my mouse, right? When the leakage current is greater than 0, then VA falls to 0. Okay, it is here in this transition here. So despite the academic stuff, because I don't really care about how does the voltage in a node vary, what are the cons of having huge dead time? So first is the voltage polarity inversion, and it is visible here, 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 here. The average voltage node shift because of these added inversions. Output power drop, as my friend says here, and the gain, that is the ratio between VOR and Vin, differs from one respect to the one we let's say designed initially. So you can see here that VOR over VP, the amplitude when they are high is different, is not one. Easy answer. I have read articles of something 50 pages to explain this. 50, not 5, 50. Simple answer. To properly restore the power, there is a certain threshold that I call the knee of this curve, in which you can differentiate the ideal DAB. So when the dead time is lower than, let's approximate to 400 nanoseconds, in which the DAB is almost insensitive to the dead time. But if your dead time is higher than this value here, you can see that to properly restore the power, so you can see the power here is locked at 480 watts like our kernel, but to properly restore the power, we need to increase angle 2. That is our epsilon axis here. So if I set 1 microsecond dead time, angle 2 is called to increase from the ideal, that is 26, to something around 51. As you can see, the power is restored. So all these green bullets actually are real cases DAB, in which we didn't bring the dead time until 1 micro because of losses reason, but you can easily using the straight line formula when you are moving beyond the knee. You can use this formula here. Here we are with the real cases, so you can see that the PSIM answers pretty good with the real case. So the solution to the dead time problem is simply keep the dead time not so short to enable the drain to source capacitance discharge for all FETs, as well as not so long, because you increase anti-parallel diode losses plus the output power drop, as we have seen here. And that's it. Keep in mind that the dead time avoided math is strongly dependent on the application. So leakage inductance related, FET selection, working condition, and so on. Hope this answer to the dead time problem.
Okay, great. Another question that I know lots of people have got is, how do you choose between LLC or DAB?
It depends. I know that it is a boring answer, but it depends from what you need to do. Actually, if you need bidirectionality, probably the LLC is tricky. This is more tricky than the DAB, because or you need to add a secondary side cap, because otherwise the output voltage of the LLC clamps the magnetizing inductance. So you need to add a secondary side cap, or move for another move. Sorry, you need to move for different modulations techniques. For sure, varying the frequency is not sufficient to get bidirectionality. So in that condition, probably I would go for the DAB current controlled, because actually the DAB current controlled, if you remove the DC blocking cap, if you don't need a secondary side capacitor, actually you have the less components possible topology, because you have just 8 FETs and you have just a leakage inductance with the magnetics. So it depends from what you need to do.
Yeah,
but again, just one note. This comparison I gave here, obviously more patent engineer noticed that I didn't include magnetic losses here. This is just transistor losses. So sorry, this is just switches losses, while the losses for the magnetics is something around 250 or 300 watts. So the efficiency is even slightly lower than 93. But again, with this example, I'm not saying that DAB is always better than LLC. Probably In this context, with 200 kilowatts with bidirectionality, I would go for the DAB. But this doesn't mean that the DAB is always greater or better than the LLC at all. In particular, let's think, for example, I give you an example for about, I would like to give you an example where the DAB cannot be used, right? And what are I mean, which kind of projects I'm working on, right? If you are okay, Ray, I would like to proceed with this. Otherwise, stop me and we can continue with the question. It's up to you.
No, go ahead. Go ahead. Looks good.
Okay.
Well, no, hold on a sec, because hold on, sorry. I thought you were going to the advanced point. Let me work through the rest of the questions before we shift to any different topics. So one of the questions, any thoughts on three-phase DAB at megawatt levels?
I didn't go through these, but I know that in particular in automotive sector, it's widely used, three-phase DAB, widely used. So imagine how complicated should be the control in that situation. But do not have any particular. I mean, it's something we can open another webinar on the DAB three-phase. There are different things to keep in mind, in particular if you are interfacing with the PFC or grid connected. I mean, it's too general question, this one.
Okay. One other question. I'm looking for more general questions here. Some of them are very specific to the slides. I would recommend that we have a community of 6,000 engineers on our Facebook group, and there will be a discussion about this afterwards, and Nicola is part of that community too. And there we have the opportunity to have a fairly in-depth discussion with schematics and pictures and so on. So I know several of you are planning on going there to continue that discussion. And yeah, I think you've got most of the questions there. So one of the questions leads you into the next part is, what about the wireless power transfer project? So one of just a quick introduction, just a quick introduction to that for you is that Nicola worked very closely with Sanjay and Maniktala, and one of the projects they worked on together is wireless power transfer, and they're using a different scheme to most companies, and it's something that you should take a look at what's showing up here, and consider this as well if you're getting into the wireless power transfer, because this is it's not a fully utilized technology at this point, and you should take it seriously. Okay, go ahead. Why don't you talk about this?
No, you touched a good point. So after Sanjaya passing, I started working as CTO with the Charge Edge and the Resonate team. For everyone which is not familiar with this little startup, it is a little company which is trying to bring on the market the most advanced wireless power transfer system. So in this short section, I have collected approximately 5 slides summarizing almost 5 years of study, designing, optimization, and prototyping. We have started having 100% grip on the LLC topology, in our opinion, the most efficient one on this subject. For lots of technical reasons, don't want to talk about the disadvantages of the competition, I don't care. I leave also a link here to my previous webinar concerning this topic. Let's follow the flow here on top. So first we got a 100% grip on the LLC. Then we mapped. We identified the flux laser magnetics disposition as the most efficient one. Sanjaya identified the flux laser magnetics disposition as the most efficient one to keep a concentrated flux versus considerable air gaps. So everything is very well protected by White and Case. Intuitions here. Okay, so here the next step has been to properly confirm our intuitions, right? Intuitions have been confirmed, modeling the complex system and analyzing its performance by using finite element analysis method. We studied the competition as well. We put their model on the bench, not just by assumption. We placed the competition model on the bench, and we really checked their system were not so efficient like declared, and were absolutely not comparable to our one. We got the feeling there was, and there is, a massive lack of understanding about the problem. And despite that, some companies continues to propose strange systems presented as potential solutions. But don't be shy to ask for proof of concept to this company. Here you can see a difference about frequency, size, and power between us and the competitors. Sanjaya, to me, Sanjaya had a gift, and he was totally unsatisfied about simulation results, despite very good, and he alone has been able to prove his intuitions in different domains. Some example here: laptop charging here on the left, lamp charging 200, it is 100 and 200 watts, drone charging here on the right, by which I have do you see my camera? Hey, do you see me?
Yeah. Hold on.
We have two drones in wireless here. Do you see me, right?
Yeah, I can see your camera. If anybody's watching it on their phone, sometimes you have to swipe left or right.
So they
You are
cannot
showing.
see. No. Later on, I will show you. And so Sanjaya was totally unsatisfied. And there are some examples here in which we tested successfully laptop, lamp, and drones. Okay, so everything has been tested with impressive results. These are facts. It's not marketing. These are facts. Everything is available on the bench.
Before you move on, Nicola, do you have any comments on the efficiency of the method?
Say it again.
The efficiency. You said highly efficient. How is that?
I would like to keep this question reserved, but you gave a penalty to me with this question, because we at Charge, we're unsatisfied even by low power tests, right? Despite positive. So we are moving further in testing Sanjaya intuition even on electric vehicle market, right? Proving that our system is the best. So here you can see the image of the flux lasers, of the flux laser for kilowatts power order. So to answer the efficiency question, I would like to keep this information private, but I can say that it's very high, respect to the classical one you are familiar with. And ChargeEdge is in any way open to any sort of collaboration. So if you are interested in work with us, please write to the mention in the contacts here, and hope to do great things together if we are interested. I would like to show the efficiency, not by talking. I would like to show the person interested which kind of level of efficiency we are able to reach. Just with this kind of answer is justified by a video, a private video that I have not been authorized to share this video with you by my colleagues Greg and Rob, because it's very private video. So I would like to share facts about in terms of efficiency with the person that is interested with. But by working on the practice, not by marketing or talking or let's say underlying potential solutions that aren't a good solutions. You know what I mean?
Okay. And I think there's two aspects to the efficiency question, is there not? There's the coupling, how good that is, and then there's the efficiency in terms of power losses.
The point is I would like to reverse the question. The point is, are you able to reach for any coupling, any load, any input bus voltage, soft switching in your device. We at ChargeEdge, we are able to do that. On 0 voltage switching on the primary and 0 current switching on off on secondary, independently from the coupling factor. That in our cases, it's not a shame to me to declare, but varies between 0.2 to 0.6 best case. Coupling factor.
Okay.
So our system is able to properly monitor and track the best working point all the times.
Okay.
Thank you for your attention. I would like to thank you, Ray, as the previous time for hosting me, and I mean your contribution to our world. I'm so happy that we are getting friends and we are moving on this field together, and as well as your suggestions and your support in this field. So thanks for hosting me once again. I recommend to join our Facebook group to all people that are not involved yet. And I mean, let's have a login even Ridley Engineering Power Supply Design Center website, because there are tons of articles in which you can learn a lot on that.
Okay, great. Thanks for that, Nicola. I'm really happy to have you, because I don't have to present every single time anymore, and that's a nice relief. Thank you. Let me just do a little poll here.
May we remove the sharing video passing to the? No, because are the listeners looking at my webcam right now or not?
I'll take control back. Okay. Just some links. Let's see.
I would like to show them my wireless power transfer drones.
Oh, okay. There you go.
Do you see that? We have low power. No, we have low power, medium power, and we have very high power. That is my one. So for everyone that is interested in working with us, simply contact Greg or Rob, and we are happy to work together.
Okay, let me grab control for a minute and show my screen, and just give everybody the easy way to go find things. Just a second. There we go. So if you go to the very last slide in your handouts,
Yeah,
I can get there quickly. We have all the links to everything, so to make your life a little easier. There's going to be a faster way to do this, but I'm doing it the slow way. There we go. Okay, so if you look at this slide here.
Yeah.
Oops, I lost it again.
I see it.
Everything on, can you see it?
No, now I lost it.
Jeez. Okay, everything on this page is clickable. So if you go to the Power Supply Design Center, we will have some lively discussions afterwards about these topics. If you want to download some articles, you can click on all of these. You can find Nicola's webinar on the LLC converter is here, if you want to go see that. And there's some books and other things that you can download. So here's a page of clicks and links for you to go look at, okay? And I was going to try and run a poll about what topics everybody else would like to see coming up in the future. We will do a follow-on LLC converter topic in about, I think, beginning of November. So I would advise you to go watch Nicola's webinar on the LLC, which will give you the background. He doesn't like to do too much math. I like to do far less than he does, because
At all.
he's younger than I am. So we would just show you the LLC converter is really interesting, because when you first look at it, the design process is just horrible. And the more you read, the more you get confused. But actually, it's a closed form design that Nicola and Sanjaya have done. And there's nothing to think about. You just load in the specs and the design comes out. And there's only one correct design point for the converter, which is really interesting, because the other converters that look easy actually have multiple design points. That one has one good design point, and it's a simple solution. So we will be doing that. Nicola will be coming back, I hope. I don't know which topics you're going to do next time.
Yeah, no problem. Actually, things are again starting to become very busy between Vigor activities, that is my first job, charged activities, that is my second job. So if we are able to, oh nice. So if we are able to manage it together, I can try to be here, no problem.
Okay. I think it would be nice when you're ready to present more data on your wireless power transfer. I think this will be a good platform for that, because I find that really interesting.
You are touching a very tricky land, you know, but we can talk privately, and for sure we can get we will find a solution, no problem.
Right. And I've just launched a poll there for everybody about which of these topics you would like to see in the future. So we will collect that poll data for a while to be able to see what we get there. We've got about 56, 57, lots of people voting. That's really nice to see. I would check my questions again here.
So actually my screen is stuck on the survey.
It's stuck on the survey, yeah. So I'm going to stop that survey.
I don't know.
Most people that are going to vote have voted. There you go. So I would like to thank Nicola so much for doing this. And
you're welcome. And if there are no other questions, keep in mind that in Italy it's 9 p.m. So if you agree and there are no other questions, I would go to have my dinner.
right, great, okay. And again, the questioning and the answering will continue on the Facebook group, or of course you can find other ways to contact Nicola.
Anyway, I suggest seriously to join our Facebook group, because there are, in my humble opinion at least, there are some highly skilled and advanced engineers in there. I mean, I'll not stop learning any time when we are here, when I stay on this platform. So I suggest, if you didn't done yet, do it.
Great, okay. And then you will all get an email from us after this. There will be a certificate for your attendance. We will send you another email in a few days, which will be the link to the recording of this. So we'll edit out the parts that.
Yeah, let's discuss. Yeah, let's discuss the recording version privately first, because I would avoid. But for sure, I made some verbal typos or some English typos, but I don't care. But just to give the reader, if there is if it is a typo in the language, it's okay. But if it is an error in the conceptual topic, I need to fix it.
Right. Okay. Sounds great. And I think with that, we will sign off here. I see we still have 280 power engineers in the room here.
200?
280 people is still in the room with us here after all these questions. So I'm sorry you might have to go back to work now, but I do encourage you, go read through the presentation afterwards while it's fresh in your mind. Oh, I see one here that's talking about a hydrogen application. And anybody on my Facebook group knows my opinion there on hydrogen. So come join the Facebook and see what we think about hydrogen. So,
Yeah.
but yeah, the choice of topology, I think Nicola, that would be a unidirectional application. You wouldn't be running that bidirectional. So
Yeah.
you have the choice of any of the topologies.
They are, I mean, I made this example because as you have seen, they are very, very similar. So even in performance, so if the performance is similar, probably I would compare the volume. And on the volume, probably the DAB could win.
Yeah. I agree with that. Okay, thanks so much, Nicola. I'm going to sign
And you guys keep in touch. Bye-bye.
And now I have to try to remember how to end the webinar. There we go.
Now we will discover that you didn't record. Do you imagine?
Yeah, we've recorded that. We're good. Thank you. Bye-bye.
Bye-bye.